And you'd be like comparing a couple different elements in these questions. Test hint number 32. Why would there be a huge jump in ionization energy when removing successive electrons from specific atoms? Okay? And I'll actually give you the ionization energies for whatever example element I'm going to throw at you. And from those energies, you should be able to identify the number of valence electrons that that particular element has, or what its common charge would be. Now think about it. We spent a lot of time in chapter 4 learning how the electrons fill in around the nucleus of an atom. Excuse me a minute while I erase. So we've got our nucleus, where our protons are, and we have that first energy level with 2 electrons in it. We have our second energy level with 8 electrons in it. Those are E's. I know they don't really look like it. E for electron. We have our third energy level. And let's say this is a magnesium atom and we have just 2 electrons out there. Okay? It's going to take a certain amount of ionization energy to remove one of these outermost electrons from magnesium. And I'm going to make up fake numbers here because I don't have tables in front of me, and that doesn't matter. You need to look at the relative amounts anyhow. Let's say it takes 200 kilojoules of energy, which is kind of low, to remove this outermost electron. Awesome. We have not changed the number of protons. There are still 12 protons in this magnesium atom, but now, with this electron gone, they're only babysitting 11 electrons. They can hold on to those 11 more tightly because there are more protons to monitor, or react, or interact with the electrons. So if we want to take away another electron, this one, it's going to take more energy. Maybe that takes, 550 kilojoules. Again, these are fake numbers. All right. Now we're down to 10 electrons being attracted by 12 protons. That's an even stronger attraction. And by taking away that other electron, we've also taken away this outer energy level. That atom has lost that outer energy level. The inner electrons are a little closer to the nucleus because of the higher effective nuclear charge. If you try to take away one of these electrons, say that one. The next value for energy is going to be pretty big. There's going to be a big jump there. And let's use the fake number 4,000 kilojoules. Okay? Because we've got 12 electrons babysitting, 12 protons babysitting or keeping track of or attracting 10 electrons, and that was a full outer shell. That was the goal of the atoms anyhow, to be stable and have that full outer shell. So to try to get an electron out of the octet, after a metal has, say, lost its 2 valence electrons, there's going to be a big jump in ionization energy to take away that third electron. Another way to look at this, and I think you can see this in the screenshot here, the configuration of magnesium is 1s2, 2s2, 2p6, 3s2. Okay? So first we got rid of this 3s2 electron, we made 3s1. That was my 200 kilojoules worth of energy. Then I took away the next one, 550, and I got rid of all this 3s stuff. Now, I'm going after that 2p6. Okay, I'm trying to make that 2p5. There's my octet. That nucleus wants to hold on to that. It's going to take a lot more energy. So when I talk about, or I ask about removing successive electrons, I mean the 3s2 to the 3s1 to the 2p6 to the 2p5, 4, 3, 2, 1, etc. Okay? It's going to take more energy the further in you go. We learned all about the order of fill to see how the electrons go in around the nucleus, so that now we can look at how they are removed, and that's going to lead us right into bonding, because this is happening as an atom is becoming part of a bond. Alrighty, test hint number 33. The trends for ionization energy, electron affinity, and electronegativity apply to specific elements. That should look exactly like test hint number 29. So the question will be very similar here in number 33, asking you about the general trend. Again, you need to know it goes to this upper right corner where the values are higher. Test hint number 34. How to identify the number of valence electrons for a specific group of elements. You have been doing this for quite a while, and we'll use that to figure out what charge the ion is going to have. Take a look at the column number. And hopefully you'll be able to see this above my column here. So column 1, the elements that end in S1 are going to have an oxidation number of +1 because they have one valence electron. They're going to want to lose that one valence electron. In column 2, it's going to be +2. Most of the D block is +2, but I'm going to put a qualification on that because we're going to learn a lot more about all of the other options the D block elements have. Over here in column 13, we have typically +3. Column 14 could be plus or -4. Column 15, -3, 16, -2, 17, -1, and 18, 0. Okay? So we have one valence electron, two valence electrons, and that's the chargeable form. 3, 4, 5, 6, 7, 8. Take a look at the columns over in the S and P block. All right, test hint number 35. How to identify the sublevel filled with valence electrons for a specific group of elements. If you know the column number, just look at what area is it in, S, D, P, or F. Okay, that's going to be an easy one. Test hint number 36. The periodic trends for the D block elements specifically. Okay. Now, most of the trends for the D block elements happen, but they are not that dramatic. So if we know that size decreases as we go across a row, it decreases within the D block as well as we go from left to right. It's just not very dramatic. It's a very gradual decrease. If we know that ionization energy increases, it's a gradual increase. So the trends follow the ones we've learned, the arrows I had drawn up here a couple minutes ago, but it's not as dramatic of a change.